Thanks for the intro, and thanks to everybody for joining us today in our webinar where we're going to talk about 3 design tricks to reduce switching noise in printed circuit boards. And before I begin, 2 quick things I wanted to mention: that a lot of what we're going to talk about today is also covered in some of my textbooks. I'll mention it toward the end as well, but if you're interested to learn more about inductance and switching noise, take a look at my first book, Signal and Power Integrity Simplified, and my last book about prototype design. Because I cover this topic about how do you reduce switching noise in all designs, and especially in printed circuit boards, in the last book over here. And that's because switching noise is so pervasive. I think it is one of the most important sources of noise to think about and design out right from the beginning in virtually all boards that you're going to build. I also wanted to mention that this webinar was put together in partnership with my buddies over at Advanced Assembly. So thanks, Advanced Assembly, for your help and support in this presentation. Here's what we're going to cover today. I'm going to spend just a minute or two talking about the principles behind switching noise, because I always say that if you have a problem and you want to solve that problem, the best way of doing that is understanding and identifying the root cause. So we'll talk about that, and that will drive our design principles of how do we eliminate the problem from the root cause. And then we're going to look at a couple of examples of what features in the board cause switching noise, contribute to it, and can reduce it. We'll look at ground bounce, power rail compression, and signals when they change return planes. And I'll bring you into my lab, and we'll see some examples of not just what are the features, but also how do we measure these effects. And then finally, we'll just summarize and pull everything together. Well, the topic for today about switching noise is really about inductance. And this is one of those really, really important principles I think every engineer needs to understand. And so I highlighted here with this little cartoon from Gary Larson. You got a couple of these cavemen, and they just shot this huge mastodon with this tiny little arrow. And one says to the other, "We should write that spot down." Well, inductance is one of those spots to write down. It is a principle that we will use over and over to kill big problems dead. And I just wanted to spend a minute talking about inductance. So here we go. We're all familiar with the properties of an inductor as an ideal circuit element, right? Here's a symbol for it. You get a voltage across the inductor only when current through it changes. That's the electrical circuit model for an inductor. And so the voltage generated across the inductor is the dIdt times the inductance, that figure of merit of the inductor. But why is that? What is it fundamentally? What is the electromagnetic reason that we get a voltage across an inductor only when the current changes? And the answer is, this is all about the magnetic field lines, the rings of magnetic field lines around the conductor. That voltage is generated fundamentally because when the number of rings of magnetic field lines around the conductor changes, that's what generates the voltage. And the rings of magnetic field lines, how many rings we get around the conductor, are related to the current going through the conductor and the efficiency of how does it turn current into rings of magnetic field lines. And that's what inductance fundamentally is. And so based on that principle, the voltage generated is related to how fast those rings of magnetic field lines around the conductor change, how many of them change, and the number of rings of field lines around the conductor is the inductance times the current. Because the inductance is a physical geometry factor, it's not going to change. And so that says that the voltage is the inductance times the dIdt. The underlying mechanism of why this is the case in a circuit model is due to this fundamental principle that the voltage is induced when the number of rings of field lines change. And it doesn't matter where those rings of magnetic field lines come from. They can come from its own currents, in which case we call them the self-field lines or the self-inductance. It can come from somebody else's current that has rings of magnetic field lines also around that conductor, in which case we call those the mutual field lines. This is the fundamental definition of a circuit element and where that comes from. And now we translate that to an interconnect. So here's an interconnect, some conductor. I put current going through it. I'm going to have rings of magnetic field lines around it from its own currents. These are the self field lines. And the number of rings of field lines around this I have is related to its self-inductance times the current going through it. That's the number of rings of field lines. If this number ever changes, then we're going to get a voltage induced. So if you look in this region of the conductor, we're going to get a voltage across this region of the conductor from one end to the other. That's related to how fast those rings of field lines change. And again, it's about the DID. And so we see that once again, the voltage across that inductor is due to the self-inductance at path times the didt. And you notice that we only get the voltage across the conductor when we have changing current. And that's where that origin of switching noise, the name, comes from. It's when do we have didt? It's when the signal switches. When we go from a high to a low or low to a high, that's when we have the didt. That's what drives the voltage across an inductor. And again, it doesn't matter where those fields come from. In this case, they're coming from its own currents. It can come from some other conductor's current if we have long field lines that go around both. So we refer to switching noise generally as noise generated by a changing current because of an inductance somewhere. Now, let's take a look at how this applies to the next example of ground balance. So here's a really simple model for the two conductors, signal and return path associated with a signal path. Maybe it's the lead in a package. So here's the signal, here's the return. And again, in the return path, we have rings of magnetic field lines around that return conductor from his own self field lines. These are from his own currents flowing this way. And we've also got field lines from the signal current that are so big and floppy, they also go around the return path. But because the currents are going in the opposite direction, the rings of field lines are going in the opposite direction around the return path. When we look at the return path conductor, we get a voltage across it when the total number of field lines change. We have that dN dt. Well, where do those total field lines come from? They come from his self-inductance and its own current, and the mutual inductance to the signal path and the current through the signal path, which, of course, if this is the signal and return, those two currents are the same. And so the voltage we get on that return path is the self-inductance of the return path minus the mutual. We call this the total inductance. It's related to the total number of field lines because, after all, when the total number of field lines change, that's what causes the voltage. And again, we see it is the self-inductance of the return minus the mutual times the didt. Again, it's the switching noise. And this is really the guideline of how to reduce ground balance, because it says we want to make the self-inductance of the return path small, and we want to make the mutual inductance to the signal path, we want to make it large because it's subtracting off. They're going in opposite direction. Well, how do we make the self-inductance small? Number one is shorter path. And number two is we want to make that conductor as wide as we can. That means a plane for the return path. Anything other than a plane is going to have a larger self-inductance to it. First step is reduce the self-inductance of the return path. Shorter conductor, wider conductor. And then how do we increase the mutual inductance between the signal and the return? We bring them closer together. Let's see how insidious ground balance is. Because this was the voltage across this return path. Suppose that that return path is shared by one or more conductors. So here is another signal sharing that same return, as is often the case. Remember, when we look at the voltage on that signal path, we measure it between the signal and its return. If that shared return is part of the path of that signal line 2, then when we measure the voltage, even if there's no signal on this, we're going to see as part of that path that ground bounce voltage. And the more IOs that switch, that share that common return path, the more didt we're going to have, the larger the ground bounce. And that poor victim line sitting here, minding his own business, is going to see that larger and larger ground bounce voltage as part of his path. And that's why ground bounce can be insidious, that it's not just the signal line that's generating the ground bounce that's affected. It's when we have the shared return, it's multiple signals going through that shared return, and it's any other signal sharing that return that's going to see the ground bounce. And how do we minimize ground bounce? It's those three important geometry features. Shorter return paths, wider return paths, that means use a plane, we want to spread that current out, and we want to bring the signals closer to the returns so that we have those mutual field-ins to help cancel out some of the total inductance on the return path. And that means lower impedance, and there will be a trade-off. Let's look at how this simple model can be applied to help us predict and understand ground bounce in a package. So here's just a really simple example, one that I show quite a bit. It's kind of the poster child for ground bounce. This is a really simple diagram of a package. So here is a die that's got 5 I/O that are switching. Here's the package that die is contained in. All of the 5 I/O share the same common rail, power rail and ground rail on the die. And there's a lead that goes from the VSS on the die to the VSS on the board. And I'm assuming that the board has a nice wide plane. So there's very little inductance from the solder ball over here where the ball is, where the lead makes contact to the ground plane of the board. Here are transmission line paths going from each of the I/O to someplace else on the board. And we're going to turn these 4 on and off. We're going to switch these 4. We're going to keep the 5th one as a low. And so that means this output is connected over here. And that means that when we go over here, we measure the voltage on this line. We measure the voltage of the signal relative to the local ground on the board, the plane on the board. We measure it. We're going to see all of these guys generating the ground bounce through this lead. So they're going to generate the DI/dt through that total inductance. We're going to see a voltage on this side compared to this side. This side's tied to ground. We're going to measure that over here. And look on this guy here, we're going to measure the voltage on this point. This entire die, this entire VSS of the distribution on the die is going to bounce relative to the board ground. And we're going to see that as this guy's voltage output. And here's the example. Here, we're measuring one of these I/O that are switching. All 4 of them are switching. We're measuring one of them, and here's the voltage on the low side. And we see that when we get current turning on, for example, we get a voltage over here that's lower than the local voltage over here. And when the current changes direction and heads back this way, we're going to get this side a higher voltage than this side. This is switching noise, only arising when the I/O changes state, when the currents are changing. Now, this method of measuring the ground bounce voltage on the die is a really powerful technique. I use it all the time, and I want to highlight again here. And this is the technique we're going to use in our example to measure ground bounce voltage. So here's an expanded view of one of those I/O, and I've drawn it as a CMOS device with P&N transistors on the output. This is going to be our victim. This is the quiet line. We're going to keep this pegged low. So that means the input, because it's inverting, the input here is going to be high. So that means the output is always low. That means that the P channel is turned off. It's open here. And the N channel is turned on. And so effectively, the output that comes over here to the board, where I'm going to measure it, the output, this is turned on. This is really low impedance. That means this point here is connected to the VSS on the die. And when I come out here and I measure the voltage on that output pin, I'm measuring it relative to the local ground on the board. I'm measuring that voltage over here on the VSS relative to the local ground over here. If there's no current through this path, the impedance of the return path, if there's no current, I'm going to get 0 volts. But as soon as I get a current, I'll get a little voltage, DC voltage drop over here, very little. Most of it is going to be from the DI/dt as other currents switch through this lead inductance. So if this is a shared return path and others switch, I'm going to see a voltage noise across this inductor. That means this point here, different voltage than this point. I'm going to see that as ground bounce voltage. This is a really powerful way of probing or sensing the local ground voltage of the die relative to the board. And that's how we're going to measure ground bounce. A very powerful technique. We call this quiet low. We pick one of the I/O as a victim line, we keep it low, we measure its voltage off the board as the other I/O switch. And that voltage that we measure is going to be due to the common shared inductance in the return path and any other mutual inductances of this loop to any of the other loops elsewhere on the board. Okay, let's take a look at the example we're going to look at. So this is one of the boards that I have my students build in our my PCB class. It's a 2-layer board, and we've got a really simple circuit. Here's a linear regulator, LDO, for 3 volts, 3.3 volts. Here's a clock chip, and I got 2 hex inverters. They're identical circuits on the left and the right side, except that you can see here I have a backlit on this board. In this region here, we've removed the plane. Instead, we have individual traces for the return path. So here's the hex inverter, here's the ground. The ground has traces to distribute the return for the IOs that are switching. I got 3 IOs that are going to switch through LEDs so we can see them turning on. We have one of the IO I'm going to use as a test point to tell the scope when do I have the IO switching. So I'm going to see them switch. I've got one that is always going to be pegged low, and so its output is low. We're going to use that as a quiet low, and in the next example I've got one that's pegged high. We'll use that as a quiet high. We'll see what that can do. So I've got the same circuit on the left side as the right side. The only difference is that on the right side I have a nice wide return plane. So remember that return path is a wide conductor, and so that means I'm going to have minimum amount of ground balance. Now, of course, I still have the package lead. This is a lead frame package, basically, even though it's surface mount. And that means I still have a common lead through this package getting to the board here where I make contact to the plane. And so I'm still going to see ground balance, but it will be dramatically reduced. I'll have the same ground balance in the package over on this side, but in addition, that return path through the board, connecting the return of all of these signal lines, that return path is going to be narrow. I'm going to have a lot more total inductance, and we'll see that as more ground bounce voltage. Now, just to clarify, this little dark thing over here, that's because I have a little rubber foot on the bottom of the board. There's no plane under here. That's just the shadow of the foot. So we're going to measure the voltage difference on the quiet low on this side with a return plane and this side without the return plane. So to do that, we're going to use one of our scopes. You know, here the example of the mid-range family of scopes we have. These are all 12-bit vertical resolution, 12-bit all the time. And whenever you're looking at noise, generally you want to try to keep the noise small, but we're looking at smaller voltages, and so the higher resolution gives us that higher dynamic range and a little bit lower noise floor in the measurement. And so 12-bit is really useful when we're looking at noise. Now, the one I'm going to use that I have in my lab is our higher end mid-range scope. This is the WavePro HD. It's got an 8 gigahertz bandwidth. And you can see they vary. They're all 12-bit. They vary by the ultimate bandwidth and the number of channels and the screen size. Here's the Wave Runner with 8 channels associated with it. So I've got 4 channels on my WavePro HD. This is really my favorite scope. It's got a nice big screen. It's touch screen, 4 channels, 8 gigahertz bandwidth, 12-bit resolution. It's got an acquisition buffer that's as large as 5 gigabits or giga samples. Huge acquisition buffer. Never used all of it. Great scope. What's not to like about it? So let's go into my lab and let's do this measurement of ground bounce. Okay, we're in my lab, and I've got the same board I showed in the slides over here. Get it powered on. You can see it's working. We're going to look at first the 2 sides. Here's the side that has no return plane. Here's the side that has the return plane on the right-hand side. And we're going to look at the signal coming off of the hex inverter when one of the IO switches. Now, we're going to look at 3 different measurements at the same time. And to do that, I've got 3 probes. And to keep them straight, you notice I have a color code here on the band of the probe. And that way, I've matched the color of the probe to the color on the scope trace. So let's take a look at that signal that's coming off of the hex inverter when it's switching so we can synchronize and trigger the scope. So here is that signal. And now I can see the scope. I've got it here in front of me. In order for you guys to see the scope, I'm running team viewers on the scope. So I'm going to tilt the camera back so you can kind of see the scope over here. So here we're in my lab. There's the scope. It's kind of awkward to be able to show both the scope and the device. And so my scope here is basically a Windows machine. I'm running TeamViewer on it and TeamViewer on my laptop, and that allows me to replicate the scope on my laptop so you can see it here, and I can control it also from the laptop. Here's that signal coming off of the hex inverter. We see about 10 nanoseconds of division, so that's a pretty fast edge coming off that guy. Okay, now we're going to look at the quiet low. That's this pin over here. That's looking at one of the I/O that's pegged low. And this is, remember, this is the side that has a good solid ground plane. So that means we are going to see some ground bounce because of the package lead, but not very much of it. So let's take a look at that in the second channel. And again, I've got the color coding here. It's the kind of the pink band here because that's the color of the second channel. So I'm going to stick it in here. You notice the probe footprints that I'm using. These footprints allow us to, there's a signal pin and then a couple returns. Allows us to use these little spring tips that are on the ground lead here. That gives a short loop and also provides a close proximity to the return. And so we use a footprint on the board that matches the signal pin and the ground return pin. Okay, so we've got the quiet low, and here you see it. And so I've got it on a scale of 500 millivolts a division. The ground bounce voltage on the quiet low is about 500 millivolts peak to peak. That means the whole die is bouncing relative to the local board ground over here, bouncing up and down peak to peak value of about 500 millivolts out of a 3.3 volt rail. So that's quite a bit, and that is as good as you can do based on the limitation of the lead frame in the package. And now lastly, let's take a look at the other region over here on the board where we have the return plane removed. On the left side here, no return plane, and so we're going to have not only the lead frame package inductance, but also the loop inductance and the common return inductance for the return path that's a trace instead of the plane. So it's a long, narrow trace that connects the returns of the ICs plus the returns of the LEDs. So let's take a look at that voltage noise. And that's going to be from this pin over here. And see, I'm going to make this, one of the difficulties of this connection is making the ground connection. So I'm going to use the next one over so we have a good solid ground. There we go. Nice stable signal. So here we see a very visceral difference in the voltage noise between having a ground plane, that's the pink, and no ground plane underneath, and just a ground lead, and that's the turquoise. And look at that. So remember, it's a half a volt per division. Here's this guy here, half a volt per division. Both of these are on the same scale. This one here is about 3/4 to almost another 3/4. That's about 1.4 volt peak to peak voltage noise, ground bounce noise. 1.4 volts out of a full scale of just 3.3 volts. Let's see what it looks like when we put them all on the same scale. So we're going to use 2 volts per division. And here we go. And now you can see all of this is the ground bounce voltage. And that's why we want to use continuous planes for the return. It dramatically reduces the ground bounce voltage on signal lines. We still have the ground bounce from the package lead. Can't do anything about that. That's where the package design comes in. So this is a really simple example of using the principle of a quiet low to measure how the die is bouncing relative to the local board ground, and how the use of a continuous ground plane dramatically reduces the amount of ground bounce voltage. Okay, let's go back to the slides. The second example is switching noise. Switching noise is about when we have a DIDT through an inductor. The second example is about rail collapse in the power distribution. Here's a really simple view of an equivalent circuit diagram of the power distribution. Here's the die with the IOs that are switching. I'm showing them here as a current source when we have the DIDT switching due to the IO signal changing from high to low or low to high. This is the power distribution. Here's the VRM over here. And I've drawn in some interconnect inductances. So here's the simple model of the output model for a VRM with a little inductance from the feedback loop and the some output impedance, output resistance. Here is the interconnect inductance from the VRM to where I have a local decoupling capacitor, and then from the capacitor to the pads on the die. This decoupling capacitor acts as kind of a virtual VRM. It's a VRM to provide the currents during the switching time of the I/O. And you'll notice that there's some inductance between where that decoupling capacitor is located and the pads on the IC, and from that capacitor back to the VRM. When this guy switches and we have a DIDT, here's this inductance. When we have a DIDT across it, we're going to get a voltage drop. And this side here is going to be tied to the voltage on the VRM. So this side of the inductor is basically tied to this voltage. when we look over here, when we have a current turning on, when this I/O switch and we get current draw, we get a voltage going this way. This is going to be the plus side relative to this side. Since this is tied to 5 volts, that means this negative side is going to drop down. And when we measure the voltage on the die, when this guy switches, we're going to see, as the current turns on, we're going to see this voltage drop. And the amount of drop depends on what this inductance is. The inductance from the pads on the die to where the local decoupling capacitor is. How do we reduce that inductance? Remember those 3 important ways. The number 1 is length. We want to decrease this length. The closer we can bring the decoupling capacitor to the pads on the die, the lower that inductance and the less the switching noise. And of course, the second way is use a plain, wide conductor from the location of the decoupling capacitor to the pads on the die. But number 1 is going to be using shorter paths. And just to illustrate that, here's that quick example. We're measuring the voltage on the die itself, and it's nominally 5 volts in this example here. We turn on this current when there's no decoupling capacitor and we have all of this inductance in that path. Oh my gosh, look at that huge voltage drop because of the DI/dt. Huge, look, it goes down to almost 1 volt. It turns that transistor off. That's when we have a lot of inductance. We put a decoupling capacitor in close proximity. We still have inductance here, but it's dramatically less, and sure enough, we have a smaller voltage drop. That's just a rough example. Now, we're going to use the technique that I showed you before, this idea that we used quiet low. Now we're going to use a quiet high to measure this on die. And so it's the same example, the same structure. Here's an I/O. We're going to make this I/O, instead of being a quiet low, turning the N channel on, we're going to make it a quiet high. We're going to turn the N channel off, turn the P channel on. So now the I/O, the output for this pin, is connected to the VCC or the VDD on the die itself. So we're going to measure the voltage on this pin, the VCC on the die, relative to the local board ground. But remember, this whole die may be bouncing because of ground bounce that's happening at the same time. And so if we measure this voltage here, we're going to get the rail collapse of the voltage on the power rail, plus we're going to get the whole die bouncing. And so really what we want to do is measure this voltage, but subtract off, because it's the local ground over here that we're measuring relative to, we want to subtract off the ground bounce voltage. The difference between the voltage we measure here relative to the local ground and the voltage we measure here, which is the local ground of the die bouncing relative to our local ground on the board, that difference is what we call the rail compression. It's the voltage between the VCC and the VSS on the die. And that's really the number that we care about. That's what the die is going to be sensitive to. And so that's the technique that we're going to use to measure the rail collapse voltage. And now let's take a look at the example. So this, again, one of the boards that I have my students build. The same circuit. Here's our clock. There's an LDO here. I'm just not showing. Here's the clock. We're going to turn this hex inverter off and on. We're going to switch it. One of the I/O is going to go to test point, so we're going to trigger the scope so we can tell when it's switching. We got 3 of them that are going to drive some LEDs. And now we're going to look at the quiet low so we get an idea of the ground bounce, and we're going to look at the quiet high so we get an idea of the VSS rail on the die and how it is changing relative to the board ground. Now in these boards, we have a continuous solid ground plane, so we're going to reduce the ground bounce voltage. There's still going to be ground bounce voltage because it's a lead frame package, but it'll be dramatically reduced if we didn't have this ground plane. So we're going to measure that voltage on the quiet high, on the quiet low, take the difference, that's the rail compression. Now in this example, we're going to look at the impact of that rail compression on the location of the decoupling capacitor, because we said if we want to reduce that inductance, we want to bring those capacitors as close as we can. We want to reduce the length and use wide conductors. Well, to illustrate the importance of that, here is the die. Here's pin 14. It's a lead frame package, so there's nothing we can do about the inductance in the lead frame to getting from the pad on the board to the pad on the die. Nothing we can do to reduce that. So here's the case where I've added 2 decoupling capacitors as close to the package as we can. And now here's another board where all I've done is I've moved those capacitors a little farther away. So I've got extra inductance in this path. And in the third example we're going to look at, here's that power path. And look, I did a really absurd thing. I moved those decoupling capacitors really far away. Now I say it's absurd knowing that, of course, the design principle is we want a short path here. That's what we want to do. But I see a lot of boards where engineers seem to want to make a neat board, and so they put all the capacitors in one region of the board to keep track of them and easy for assembly without any regard for what's good for performance. And so this is clearly not something we want to do. So we're going to go in the lab. We're going to measure the ground bounce. We're going to measure the rail collapse. We're going to take the difference, and that's going to be the rail compression. And we're going to compare this board, this board, and this board. And of course, you would expect less rail compression in this case, a little bit more in this case, and a lot more in this case. Of course, we're still going to see rail compression because we've got the inductance of the lead frame. And now the last thing that we're going to do after we do this is we're going to look at, okay, we're measuring the voltage noise on the die. What would we see if we looked at the voltage of the power rail on the board? And I have a test point over here that will measure the voltage, the 3.3 voltage on the board near where the LDO is. And we'll compare that voltage with what we get on the die. Now you think, oh, they're all the same net. They are literally the same net when we design the board. Why wouldn't they be the same? Well, that's because we have a little bit of inductance here between the die that we're going to measure and where the nearest decoupling capacitor is, but we have a lot of inductance getting to the test point. Even in this case, we have inductance over here, but we have a lot of inductance going this way. We have built a filter. The noise over here has to get through this inductance and this capacitor to be measured over here on the board. That L in this path and that C, that is a low-pass filter. And so just because we measure voltage noise on the die doesn't mean we're going to see that on the board because of this filter. And we'll see the dramatic difference between the noise that we see on the die, which is what the I/O cares about, and the voltage that we measure on the board. And that's why just because you measure voltage noise on power rail on the board doesn't tell you that's what's going on the die. That's why these measurement techniques are so important. So let's I'm going to bring you into my lab. We're going to do the measurement on these three boards. Okay, we're back in the lab. I've got one of the boards here. This is the board that has the decoupling capacitors in close proximity to the IC. We're going to be measuring 4 places. So let's go ahead and do that. So first we're going to look at the signal coming off of the hex inverter that's going to trigger the scope. So again, we'll look at that. We got color coding here. This is the yellow band, and that's going to be trace 1 or channel 1. So we're looking at that signal on the scope. And just so we can bring it on the side here, let's go ahead and grab that, and we're just going to drag it over to the side so we can see it. And here we have that signal. This is going to be our trigger telling the scope when the IOs are switching. And we're going to look at the noise synchronous with that trigger signal. That's another important technique to use when you're looking at switching noise. There's always going to be some signal that the noise is synchronous with to distinguish what is the switching noise. Trigger the scope on one of the IOs that's switching so you can capture that edge. Next, let's take a look at the quiet low. So that's going to be, we're going to use the next channel. That's the pink trace. So we're going to look at the quiet low. So once again, let's move that trace of the quiet low over to this side. And there we are. And I'm going to expand the scale. They're all on the same scale right now. I'm going to go up 1 click. Let's go to, we'll make it half a volt per division. So that is the quiet low. That's the ground bounce voltage that we saw before. We're going to be subtracting that off. The third trace is going to be the quiet high. And that is this guy over here. Let's take a look at that signal. This is the noise on the quiet high, which is really the power rail. And to show that, let's bring that onto the scale, and we'll make them the same scale. And here it is, and it's a 3-volt signal, but you see it popping down. It's a 3-volt signal, so we're going to zoom in on it. So we're going to move this down into the center. Then we're going to expand the scale. Let's see, let's go to 500 millivolts per division. Okay, and you can see that the rail collapse and the ground bounce are of comparable value, but they're not switching the same. When we subtract them off, we're going to see the rail compression on the die.
So let's do that. And to subtract them off, so we see the real compression, I'm going to use a math function, and we'll use F1. Let's see what we have on F1. We don't want FFT, we want simple math. And so we're going to go to basic math. We're going to take the difference. And here we have the equation. We want channel 3, that's the power rail voltage. And we're going to subtract on from channel 3 the ground balance voltage. And that's going to be the difference, and that's what we're going to display on F1. And there we are. Okay, and you notice we got the same scale. Everybody's at 10 nanoseconds per division. We've got the 500 millivolts per division. That's the difference voltage. It's a little busy here. Let me expand out just one click so we can see that a little bit better. Okay, and so what we really care about, the rail compression on the die, is the yellow trace over here, the orange trace. And oh my gosh, you know, see, we're at 500, that's a half a volt per division, and we are 1, 2, almost 2.5 divisions. So that is about 1.2 volts peak to peak as the rail compression on the die when that edge switches. And that is, let me remind you, what we're looking at, that is the case when we have the capacitors really close, limited by the lead frame itself. So we have 1.2 volt rail compression on the die. While we're here, let's look at the voltage on the board. The 3.3 volts on the board, close to, here's the LDO, and here's the connection to the output. We're going to measure it right off over here. And remember, we're looking right now, the rail compression on the die, we're going to measure on the board. Let's see what that is. Here comes channel 4, and again, it's the green color coding. That's going to be the green trace. This is the voltage rail on the board. Let's set the scale to be the same. So here are half a volt per division. Let's move them over here so we can compare. So we're looking at the rail compression on the die. Here it is in orange. And here's the voltage noise on the board rail. And you can see a dramatic difference, much less. If we were looking at just the noise on the board and say, oh, well, we've got, you know, maybe 100 millivolts peak to peak, maybe 200 millivolts peak to peak out of 300, if we were looking at just the board and said, oh, we have about 200 millivolts peak to peak on the board, we have got about a 3.3 volt rail, we'd say, that's not bad. That's a pretty good, pretty low amount of voltage noise. But look at how much voltage noise we have on the die itself. And we would never know that unless we went looking for it. Well, now that we have everything set up, I'm going to simplify it a little bit. We only care about the difference. I'm going to move the quiet high and the quiet low off the screen so we can do a better comparison. So the orange is the rail compression on the die, and the green is the voltage noise on the board. Okay, so this is what we've got in the good case. This is the case when the decoupling capacitors are really close to the IC. Given this, now let's take a look at the other two boards. And all I have to do is plug the board in and plug the connectors in. So I'm going to do that really quickly, and then we'll do the direct comparison. And here we are back again. And now we're looking at the case where the capacitors are a little farther away. And sure enough, look, we have very little voltage noise that is on the board. In fact, it's less on the board. But look at all the rail compression we have. It's almost 3 divisions, 1.5 volts of rail compression peak to peak when the I/O switch. And that's what the capacitors moved a little farther away. We have this extra amount of loop inductance in this path. We've got a little bit of filtering because of this inductance and these capacitors of the noise on the die getting to the rest of the system. And now let's look at the third case. And here we are back with the third board. We've got the decoupling capacitors really far away. We've got a lot of inductance in this path. And look at the noise. Here's the rise time. Look at how much rail compression there is. Oh my gosh. Remember, everybody's on a half a volt per division. So there's 1, 2, there's a volt and a half, almost a volt and 1.2 volts of rail compression on the die because of the large inductance in this path and the DI/dt. It is so large, it's dramatically distorting that rising edge. We're almost turning the transistor off with that large voltage drop out of the 3.3 volt signal. This is the voltage noise on the die. This is the voltage noise on the board. Yeah, there's a little voltage noise on the board, coincident with the I/O switching, but it's a tiny amount compared to what we see on the die. This again is why it is so important to be able to measure the noise on the die, because that's where the action is. There's a filter, a built-in LC filter, two-pole filter, between the noise generated on the die and the rest of the board because of the inductance of the lead getting to the capacitor and the capacitance of the decoupling capacitor. That's why we always want to be doing these sorts of measurements for rail compression. Now, let's return back to the slides.
And now I promised you 3 examples. The third example we're going to look at is when we do a 4-layer board and signals can change the return planes. And so I've got examples here. This is taken from my textbook. I've got examples here of the stack up for a 4-layer board. These are different stack ups. Which one should you use? Well, depending on the application, all of these may work, but some of these different options have lower noise than others. And it's a really important principle to keep in mind that just because a previous design worked, it doesn't mean it was because of what you did. It could be in spite of what you did. And if you're not measuring the noise, you have no idea what the relative amount of noise is between these options. And it may be that the design you built with, this option or this option may have worked because you didn't have very many signals switching, you didn't have much DIDT, and it was a marginal design, or you didn't exercise it enough, and the next time you ran that or other code that you might run, you might get an error. And so if you don't measure the noise, you don't know the relative performance. And of these options, we're going to compare these two. We're going to look at the case where we have 2 return planes that are the same voltage. In this case, we're going to peg them low at ground planes. And we're going to compare that with 2 planes, a ground and a power, in which case we don't have a connection, a DC connection between them. So we're going to look at the impact of the plane selection on the noise generated, the switching noise, as signals change layers and the return plane changes as well. Here's what I mean. So let's take a look at the case where the 2 planes are not the same voltage. Here's a cross-section view. Here I have microstrip signals on the top layer. They go through a via to the bottom layer. When they do that, when they're on the top layer, their return current is on the top plane. When they're on the bottom, their return current is on the bottom plane. And I provide a via for the signals to transition from the top to the bottom layer. But how do the return currents get from the top plane to the bottom plane? Well, in a convoluted way. Here's the signal return, signal return, signal return, signal return, signal return. Uh-oh, I have to get over here where it's signal return, signal return. How does that return current get from this plane going this way to this plane going that way? Well, it gets through it by the cavity, the impedance of the cavity. So it's signal return, and it's going to go from this plane to this plane. There's some impedance between these 2 planes, and the return current is going to flow signal return. It's going to flow between these, snake around, and then it's going to give its continuity. So it'll be signal return, snaking around, heading back up. And that means I have return current now trapped in this cavity between the 2 planes. And it's going to propagate. And as it propagates through that impedance, it generates noise between those 2 planes. And any other signal that also passes through those 2 planes is going to see that voltage noise of the planes as part of a signal path. It's a type of ground bounce. It's a type of return path bounce. It's due to the impedance of the return path, and all of these paths, the pass through the cavity, are common to all the other signals that are transitioning from the top to the bottom. And the more DIDT, the more noise I'm going to get in the cavity, and my other IOs are going to see that pass through the cavity. And how do we fix that problem? Well, the way we fix that is we want to reduce the impedance of the cavity. The best way of doing that is adding a shorting via. And when we add a shorting via, then that's always going to give us the lowest impedance path. So, and of course, now that we know it's about the inductance of the return path, what is the number one thing we want to do with that? Keep it short. That means we want these 2 planes as close together as we can. The second thing we want to do is we want to keep it wide. Well, that's where the via comes in, or multiple vias to reduce that total inductance. And the third thing is we want to bring that return path, that shorting via, in close proximity to the signal path. And so that says, whenever we generate a signal via that goes from the top layer to the bottom layer, we want to add a shorting return via. to do that, I've got to have the same voltage on these planes. And that's why the number one most important principle to reduce switching noise is we want the two planes to be the same voltage so that we are able to add the shorting via. If these are two different voltages, here's power and here's ground and here's a 5-volt plane, if they're different voltages, we can't add a shorting via. And so you say, well, I'll just add a decoupling capacitor between them, a short with a DC block. That's a fallback position, but that inductance of the capacitor with the two vias connecting the top plane and the bottom plane up to the top surface, that path is always going to have much higher impedance than a simple shorting via. And so if you want the lowest noise, you always want to use the planes of the same voltage to enable us to add that shorting via. Doesn't mean that it's not going to work if you make them power and ground planes and you have the capacitor. It won't give you the lowest switching noise. So we're going to take a look at a measurement of this type of noise. And again, I got a couple of boards that I use in one of my classes. And we talk about this in the textbook about building prototypes. Here is one of the boards. And on this board, they're all 4 layers. The stack up is signals on the top and the bottom, and I have 2 planes inside the board. And the second plane, I'm going to float that plane. It's not going to be connected anywhere. When the signal's on the top, it uses the adjacent plane as its return. When the signal's on the bottom, it uses the adjacent plane as the return. And on this board, I've got another simple circuit. I've got a clock generator. Here's the top view of the board. I got the clock generator. And on the bottom of the board, I have these 2 hex inverters. And all 6 of the I/O are going to drive signals from the bottom layer. So here's the signals, the I/Os, traveling down the traces. They have vias that go to the top layer. And on the top layer, they go through LEDs and resistors so we can see the I/O switching. So I have 12 of them switching, and I've got an 11th signal line here that is just a signal line shorted at the far end to ground, to the ground plane, and it goes through a signal via as well, and it's going to go through, here's the bottom layer, it goes to this test point over here. And so we're going to measure the voltage on that signal line going through that cavity shorted to the ground over here at the other side. And when all of these I/Os switch, they get all of their DI/dt going, the signals go through the vias and through the traces and through the LEDs back to the ground plane, and their return currents are going to flow from the bottom plane to the top plane. Now, I have 2 versions of this board. I have one version where I have return vias between or adjacent to all the signal lines. And so that return current in the cavity from the bottom plane to the top plane is going to flow through those shorting vias. That's one version of the board. And I have an exact duplicate of that board, only without the shorting vias. So there's no shorting via between those signal lines. It's just going to be between the floating plane. And I'm going to look at the noise on that victim line, that quiet line that's just sitting there minding its own business going through that return plane. I'm going to measure the noise of that victim line when I have shorting vias and when I don't. So let's again go into the lab and we're going to measure that voltage noise on this poor victim line when I have a return via adjacent to every signal and when I have no return vias between the 2 planes. Here's our last example. This is a 4-layer board. This particular board, on the bottom side, we have the 2 hex inverters. So there's 12 I/Os altogether that are traveling around as microstrip. Signal and return is the adjacent plane. They go over to the signal vias. You've got 12 signal vias over here. On the other side of the board, those signal vias come up top microstrip trace. They go to LED, to resistor, and then to ground. And so we drive current, maybe about 30 milliamps of current through each of these. So we get 12 times that's 1/3 of an amp of current that's going to flow. The signal current is going to flow between the bottom layer, bottom signal layer, and the top signal layer. And the return current, that's 1/3 of an amp of return current that's going to flow between the bottom plane, which is layer 3, and the top plane, layer 2. And how's it going to get from layer 3 to layer 2? Through the impedance of that cavity. And as that return current spreads out, that return current is going to generate a voltage drop because of the current through the impedance of the cavity. That's going to generate a voltage
between the two planes that make up the cavity. And we've got this poor little victim line over here that is going from the bottom. So here's the test point on the bottom, goes underneath the rubber foot, comes over here. It goes through the board from the bottom layer, through the board, through the two planes to the top layer, and then comes over here and it gets shorted over here to the ground plane. So the bottom plane is a floating plane. There's no connection to it in this board. And we have a victim line that goes through the same path that the signals do. And so we're going to drive all those signals. They're going to come up through the signal vias. The return currents are going to drive between the two planes through the impedance of that plane, generating noise. This victim line is going through that path. We're going to measure the voltage noise over here. Now, to trigger the scope, we want to see when those currents switch. And so we're going to look at the voltage across one of these resistors. That's going to tell us when the I/O is switching, and then we're going to look at the voltage noise over here. So let's plug it in. And it's on, and those LEDs are pretty bright LEDs here. We got a lot of current flowing through here. Here, again, we're color coding. Here's yellow. This is going to be the voltage across that resistor. So it's going to tell us when the I/Os are switching. I'm only looking at one of them. And so here we go. And we're looking at the scope trace. And here's what the signature of that current looks like. And I'm just going to zoom out a little bit. And you can see this is the way the I/O is turning on. We get a little current surge. That transistor turns on hard. We get a lot of transient current, and here's that steady state current coming out. And the rise time, you can see here is, here we're at 2 nanoseconds of division. So the rise time is about a nanosecond or so. So it's a pretty fast edge. And now we're going to look at the voltage noise on that poor victim line. So here is the victim line over here. And we're using the blue color code here. So we're looking at this channel 3. I just happen to have the blue one handy, so that's why we're going to use it. So we're going to look at the voltage noise on that blue line. Remember, this is with no return vias. And oh my gosh, there's a lot of crosstalk. Now I'm going to make a little better connection here. Here we go, a little more stable. Now, just so that we can compare, look at this voltage noise. We're at 100 millivolts per division. And so that noise between the two planes goes up 1, 2, 3, and down 1, 2, 2.5. So we have a voltage noise in that plane of about a half a volt peak to peak voltage, a little bit more than that. Let's save this so we can compare this with the board that has return via. So I'm just going to save that waveform. Come over here, save waveform, and we'll save it. Let's see, it's channel 3. We'll save it into memory location 1. And there it is. We'll keep it over on this side. Let's move it over to this side just so we can compare it. Now we're going to replace this board with the board that has return vias and see the dramatic impact of that half a volt switching noise in this board. Here is the second board, and now you can see wherever there's a signal via, there's a return via adjacent to it. Otherwise, these two boards are identical. Let's plug it in. Got a nice bright green LEDs. We're going to look at the current over here through the LED. That's going to trigger our scope. There it is, same signature we had before. And now we're going to look at the noise on the poor victim line that's going through this cavity with all those return vias. And you can see that, oh my gosh, there's some noise there, but it's dramatically reduced. And these are all on the same scale. Yeah, there's some noise in that cavity. Hey, you got some inductance in the return path there. You got a lot of current switching, but dramatically reduced. Instead of having 500 volts, it's less than 50 millivolts peak-to-peak noise in that cavity. That's why you want to have a return via adjacent to every signal via, if possible. And in order to implement that, you need the same voltage for the two planes that make up the return planes in this 4-layer board. That's why it's valuable to use 2 ground planes in the board so that we have the opportunity to add those return vias as needed. Okay, let's return to the slides and pull together what we've talked about. So with that, thank you all very much for joining us. I'm going to just summarize what we've talked about here from the principles and from the measurements. So again, keep in mind that we oftentimes have to make design decisions. And there are a lot of choices that we have to make. Most of the design decisions are a balance of trade-offs. We worry about noise, we worry about the impact of the cost, the risk, the schedule, supply chain. A lot of different factors go into making those decisions.
Once we establish connectivity in the design with the interconnects, the only thing the interconnects are going to do for us is introduce noise. And so interconnect design is really about reducing the noise. And if you don't measure the noise using some of the techniques I've showed you here, how do you know how much noise there is? It's hard to make those decisions based on your experience if you're not measuring the noise. And if the noise is generally below some acceptable level in your design, and you're not measuring it, your design may have worked even though there's noise there in spite of your design choice, not because of them. Or maybe the specific test vectors that you use didn't exercise the worst case noise, in which case the customer is guaranteed to find that combination of I/O switching and code running that's going to exercise the worst case and give you that noise. And so it's really important to be able to measure the noise that you've got in your system. And so how do we balance those trade-offs? You got to understand those design choices based on the fundamental principles and by doing estimates, putting in the numbers. You want to explore design space with virtual prototypes. That's using simulation, which is a little more complicated, or well-characterized real prototypes, and that's what we illustrated here. If your design decision reduces noise and has little impact on the other costs, you should always do it. What's not to like about it? It should become a habit. Now, you'll notice that so much of what we've talked about today is about inductance. This is the pathological, I've shown you 3 examples of kind of pathological crosstalk generated by inductance. And how do we reduce it? It's about engineering lower inductance in the past. That means you want to reduce the loop inductance for power to minimize power rail collapse between the pin on the IC and the nearest decoupling capacitor. We looked at where common shared return path inductance generated ground bounds. Anything other than a wide continuous return path is going to have higher total inductance for that return path. We want to use planes wherever possible and watch out for that mutual inductance between other signal return path pairs. Now, because inductance has been such an important topic for today, I want to highlight for you, if you want to learn more about inductance and understand how the physical design influences inductance, I have a whole chapter on that physical basis of inductance in my textbook, Signal and Power Integrity Simplified, and so you want to check that out for sure. And while you're looking for other references and want to learn more about this and other measurement topics, be sure to check out all the other webinars that are available from Teledyne Lecroy. Go to our website, click events, you'll see a selection of all the different content that we have available. You can search under webinars and you'll see a listing of all the upcoming webinars as well as all the previous webinars, the on-demand webinars. They're all completely free. So if you're interested in measurement techniques and these design principles, be sure to check out our webinar page. And then finally, I also mentioned that the software that I was running on our scope, the Maui Studio software, you can download a copy of that. Go to our website. You can download the Maui software. You can run a scope emulator on your PC and practice some of these techniques that I showed you here. And with that, I'm going to throw the floor back for questions. Thank you all very much for joining us and look forward to meeting you in person one of these days.